We're now going to go run the do file and see in more detail what these things were doing.
Right.
So to exit this do file, since we don't want to edit anymore, we'll just hit the X. We're back here in MLAB, and we want to execute this do file. Now, this is in our examples list, so we could have started MLAB again and gone through our examples and run the Hodgkin Huxley example. But instead, we're just going to run it directly. So we say do quote examples. We know that's the name of the directory it's in. do ex.do quote. Okay, and that should go execute that file. Here goes. And here it's running. And the first thing it does is it echoes the contents of the do file. So it echoes this initial comment, /* through the // which is right here. There's the */. So it says this example will solve the Hodgkin-Huxley differential equations, and it's pausing, waiting for you to read this, and having read it, you did read it, didn't you? Okay, we then hit a key, any key, so the return key will do, and the program, that is the do file, continues to execute. You saw this text roll by quickly. All of that text was graphics text, which was drawing this picture. This picture is the Hodgkin-Huxley model as an electric circuit. In fact, it is an electric circuit model. What this is a little patch of cell membrane on a nerve axon. This is inside the nerve, and this is the space outside. In the outside space and the inside space too, there are potassium ions, K, and there are sodium ions, Na. These are doubly charged, of course. And there are other ions, leakage ions, including chlorine, not much, which are predominantly have a negative charge. So these have positive charges, positive charge, negative charge. Now, because there are, in many cases, an unequal amount of potassium ions on the inside and the outside, and also an unequal amount of sodium ions here and there will be a tendency for potassium to diffuse through little holes in the membrane from the side which has the most potassium. So it will diffuse from the high concentration to the low concentration, just randomly, not because anything is driving it. And in this case, the natural diffusion is from the inside to the outside. Whereas the natural diffusion, see the little arrowhead there? And the natural diffusion of sodium is from the outside to the inside. Leakage goes the other direction. Okay, these the force of the diffusion, that is the difference in concentrations provides, is described by a little battery. We think of it as an electric battery providing a voltage of a certain direction, in a certain direction. So you see this is the battery for sodium, this is the battery, or sorry, for potassium, this is the battery for sodium, this is the battery for leakage. Each of these is a function in the mathematical model description. And because this membrane is only slightly permeable to these ions, it acts like a resistor. So here are the resistors for those three diffusion paths of ions. And these resistors change. They are not constant. What happens is that as an electric field is created by the moving ions, it actually causes molecules in the cell membrane to rotate and open a hole, called a channel, and let the ions diffuse more rapidly through the channels, which in turn changes the electric field, because the motion of ions is an electric field, creates an electric field, and that causes the gate molecules to rotate closed again, and that stops the rapid diffusion of ions. What happens is you have a ring of open gates, you have high diffusion, back and forth, high current, therefore high voltage, and then that closes the gates and opens the gates nearby, because that's a different electric field nearby. And that ring of opening and closing gates moves down the cell membrane. So just imagine these little molecules in your axon going open, close, open, close, open, close, moving down, down, down the axon so fast you can hardly imagine. And that is a nerve impulse. Mm-hmm. At the other end, of course, that impulse causes the release of synaptic carriers that continue the process of transmission, but that's another story.
Right. So why is this model useful?
Well, it's useful because it describes very carefully exactly what you see in a nerve. If you've ever had carpal tunnel, you may have had a nerve conduction test, which will see whether or not you have the standard action potential picture in your pinched nerve. But at any rate, and by the way, this same electrochemistry, that is, gates opening and closing and charged ions moving back and forth across membranes, is ubiquitous in physiology. Your muscles work this way, your heart muscles work this way. It's not just nerves. But at any rate, this membrane also is a capacitor. That is, since it is blocking the motion of ions, ions will pile up on the inside and on the outside, opposing one another in order to act exactly like the plates of a capacitor do. Now, the other thing about this circuit model of the membrane patch is that there is an applied voltage which is actually done by putting fine needles inside and outside the patch and driving it with a complex circuit that actually applies the exact voltage we need to establish a given current, to set up various experimental conditions. One of the great proofs of the Hodgkin Huxley mathematical model is that it exactly describes what happens in a real patch of membrane when you apply various experimental voltages across the membrane. Now, when Hodgkin and Huxley did this original work back in the early 1950, they used the patches of membranes from a giant squid because the giant squid has giant axons, and it was easier to put electrodes inside axons when you were working with a giant squid. But at any rate, we're now going to see this model actually solved and show the so-called action potential, the so-called solution. But what we've just seen in MLAB so far are the commands that did this picture. So this picture is explaining to you graphically what the model is. And now we're going to come over here and hit a key, and we continue. The picture goes away because we have an unview in our script, in our do file.